what does high resolution mean? NMR spectrum of an organic compound does not generally consist of a series of single peaks. Rather, it has multiple peaks, but they are shown in what is known as a low spectra, okay, or low resolution spectra in this case. So instead of a sensitive high resolution NMR machine, so what happens in that case is it basically zooms in and opens up the peak. For example, if you look at the peaks in this case, the CHO peak is quite constricted in this case, and you can't see. Even if I zoom into it, can you see? It's slightly more difficult in this case. What happened? Yeah. Can you see now? Right? If I zoom in more, then you can see
Yes, sir.
slightly better, but it's still pixelated. Do you know what what this means? That using a high
Right.
resolution spectra or a high resolution NMR machine, you can reveal the actual set of peaks in this case. Okay. So let's try to understand how does
Okay.
that happen. So first thing is the high resolution NMR peaks can be obtained by applying effective magnetic field. Okay, so the splitting of the peaks in this case, basically splitting of the peaks is what we call uh, into the resolution. Okay, so zooming into or into the resolution is what it means. So splitting of the peaks occurs as the effective magnetic field experienced by a particular nuclei is modified by the magnetic field produced by the neighboring protons. This is what is known as spin-spin coupling. So basically what happens, the atoms, so when the peaks are being formed, okay, or you can say that the corresponding peaks are adjusted due to the effective magnetic field. Let's say if there is a single carbon atom which shows a particular peak, or in NMR, it will be hydrogen, right? So the surrounding atoms also produce a specific, you know, peak in this case, okay? And they modify the magnetic field around this hydrogen. So because of this, it causes what is known as spin-spin coupling. And there are certain things which happen here. Here, the magnetic field experienced by the proton in methyl group, for example, depends on the spin of the proton of attached to the carbon atom of the carbonyl group. Okay. So the molecule in this case is ethanol, right? But if you draw the ethanol molecule, C double bond O and then H, right? This is the molecule. Okay, so it depends on the spin of the proton uh, attached to the high carbon of the carbonyl group. So the peak of this hydrogen is dependent on this hydrogen. Okay, is that clear, Nessa? That's what it is telling you. The local magnetic field is increased. So the local magnetic field is increased when the magnetic field of CHO proton is aligned with the external magnetic field. Hence, decreased when aligned against it. So as the energy separation between the two spin states of a proton depends on the local magnetic field, this results in two possible values between the nuclear energy levels of CH3 protons here. Do you understand? All right, I'll come back to this, but first understand this, what this means. So the magnetic field produced by the hydrogen in the CHO group, right? It will be significant in this case. It increases because it aligns itself with the external magnetic field, right? So increase local magnetic field in this case, and it is also aligned. So therefore, there will be a specific set of, difference in this case. Then there will be a second peak, which will be caused by decreased magnetic field. How so? The magnetic field of the hydrogen in CHO is aligned with the external magnetic field, but not with the magnetic field produced by hydrogens of the CH3 group. Okay, so it will then produce another peak in this case. Okay, so because of this energy difference, you will then get two particular peaks, right? Instead. So instead of one signal to one energy difference, you will instead get two signals corresponding to both the energies in this case. Okay. So each line corresponds to a different spin of the neighboring proton. As they are both equally likely, the lines are of equal intensity. Okay. So we'll understand as we move forward what happens when you have multiple hydrogens around it. Okay. Now please understand, in order to define it, we must first of all come across which hydrogens are which. Okay. So what sort of type of hydrogens are present there? You remember we did sampling of hydrogens in this case. So if they are attached to this carbon, they will be different than the when they are attached to the next carbon. Right, Nisa? Okay. So
Yes, sir.
this is the part. In a similar way, the low resolution peak corresponding to the CHO is split due to the different magnetic fields produced by the combination of the spins for three protons of the methyl group. Okay. So there are how many possibilities? There are 2 to the power 3 possibilities in this case. Okay. So the produced signal that you will get will be with intensity will be 1, 3, 3, 1. Okay. If you add them together, it will be the same as 2 to the power 3. You can add it. All right. Basically, what it tells you that due to the coupling of the hydrogen atom, okay, if let's say there is one hydrogen atom which will give a particular peak. So it is because of spin-spin coupling, it will be affected by a nucleus of other hydrogen atoms around it. Okay. So if there is one more hydrogen atom in this case, it will give you 1:1 peak. Okay. So therefore you'll get two peaks. In one case, this first of all the coupling of the other hydrogen atom will be with the respect to or aligned with the magnetic field, external magnetic field. So that will always be there. But then there can be two situations. In one case, the spin of this hydrogen can be uh, with the spin of the magnetic field and the other hydrogen atom, or against the magnetic field of external magnetic field and external hydrogen atom in this case. So therefore it results in two peaks. But if that is the case with three sets of hydrogens, then you're calculating a total of 2 to the power 3 combinations. Okay, so you'll get 1, 3, 3, 1. Okay, that's how you'll get the peaks in this case. Right? So the
Yeah.
possible set of orientations are written at the bottom. You can see. So
Yeah.
two protons, like all three protons align with the external magnetic field. Uh, all three protons are against the external magnetic field. Meanwhile, with the external magnetic field, you're also considering that the hydrogen attached to the CHO is also aligned with uh, the external magnetic field here, right? So what is the splitting pattern of produced by neighboring hydrogen atoms in this case? Okay, since there are two hydrogens here, so the splitting pattern will be 2 to the power 2. Okay, so by that, the number of combinations that you can have is 2 to the power n.
Okay.
Here,
That was what I was about to ask. Would it be always 2 to the power, whatever the number of hydrogens they've
yeah,
given
yeah,
us?
it will always be. But the thing is, look at how the intensities have been lined up. Intensities will be in with respect to three lines in this case. Okay? The
Okay.
combinations will be four, but the intensities will be three. Okay. How so? Because look
Understood.
at the first and the last one. They are either with or against, right? But then there can be two sets of combinations which are equal in approach. Okay. So because they are equal in approach, they can be stacked up on top of each other. Hence, the relative intensities give you three different peaks. Okay. Three lines
So it is
produced with
basically the number of like all the possibilities of
hmm,
like the spin, right?
yeah. Okay.
Okay.
Here is a good understanding of how you can figure it out. Okay. So depending on the number of hydrogen atoms, the splitting pattern will be relative to that and the intensity will be relative to that. For example, if there are 0 protons, which cause pretty obviously there will be one peak to it. But since there is no hydrogen here, there will be no intensity associated with it. You understand? Right? Okay, and this is what is known as the
Yeah.
Pascal's triangle. Then you have one hydrogen, so it will give you 2 peaks. Both of these will have 50%, ratio, isn't it? 1:1 ratio in this case. All right.
Yeah.
If you have 2
Right.
peaks, 2 hydrogens, then it will give you 3 peaks of the ratios 25, 50, 25, likewise. Okay. 3 peaks. So 33.
All
Uh,
right.
no, no, no. This is what? How would you define it? 1:2, 3:2, 3:1. So, I mean, you do the math, you get the point what I'm trying to say. So it's like a pyramid scheme which is formed,
Yeah,
right?
understood.
So, when analyzing high resolution NMR, the following additional points should be noted. First of all, protons bonded to the same atom do not interact with one another as they are equivalent. Okay. Is that clear? Protons bonded to the same atom do not interact with one another as their equivalent and behave as a group. Protons on non-adjacent carbon atoms do not generally interact with each other. So if you're considering two atoms which have hydrogen atoms, but they are not close to each other or they are not adjacent to each other, then they will not interact with each other, and therefore no, coupling will happen. Clear? Okay, next one, OH. So this is done. Then OH single peak in ethanol does not split unless the sample is pure, as rapid exchange of proton between ethanol molecules averages out the different spins. So basically what it means is that in case of ethanol, okay, the proton here, if I write the formula CH3, CH2, and then O and then H, this particular hydrogen atom tends to, displace from one side to the other. Okay. And the exchange that happens here is quite rapid. So much so that there is not enough time for the coupling to happen. Understood? You will get a peak because of the, intensity, because of the spin of the nuclei. Okay, so that will give you one particular peak. But the problem with this is that because the OH bond is polar, it will cause the exchange of proton in this case. So that is not enough. There is not enough time for the spin coupling to happen. Understood? Got my point? Let's move ahead. Okay.
Yeah.
So here is an example. Okay. So the empirical formula of the compound is already given. The peaks are already given. So we need to figure out what does that mean. Okay. So in this case, the formula is given. What is the question? Deduce the molecular formula of the compound. Draw the possible structures of the molecule with this formula and use the section. Okay, blah, blah, blah. Let's first of all figure out what is the molecular formula of the compound. Okay. So shall we do this, Nisa? Let's see if we can figure this out or not. So I'll write the groups here. So this would be CH2, right? ठीक है. यहाँ पे कुछ होगा, यहाँ पे कुछ लगेगा. Okay. So this is a single peak. So that means the
Okay.
peak with this is CH3, right? Isn't it? And this particular peak
Right.
refers to 3 hydrogens in this. Sorry, 3 peaks refers to 3 hydrogens. So this is relevant. So this is CH3. This is how it should look like. Okay. Now, how do we start this? Let's start
Right.
with the first part. It is an ester. Okay. Okay. It is an ester because
Yes.
if it were to be a alcohol or a carboxylic acid, it must give 2 more single peaks, and that would correspond to 1 hydrogen each, right? We are not getting either of those, right?
Right.
Yes, sir. So that's not possible. So that means this is the
Right.
scenario. It must be an ester. Now let's start with the let's start with this peak, okay? The one in the middle. So this peak means if this is the case, then what is attached to it? If you read the second point from the sorry, the first point in this case. protons bonded to the same atom do not interact with one another as they have, sorry, second point. Protons on non-adjacent carbons do not generally interact with one another. Okay. Now,
Right.
how does this work? If let's say there is no, if this is also carbon or this is oxygen, whatever it is, there are no hydrogens on top of it. What does that mean? It means simply that since there are no hydrogens on top of it, what will it couple with? Okay. The idea or the peaks that you get, the number of peaks that you get are with respect to the hydrogens on this carbon and not the carbon before it. Yes, sir. Do you
Okay.
understand? So
Yeah.
for this particular carbon and the hydrogens attached to it, you are getting the peaks here. You understand my point? Okay.
Yeah.
So that is only relevant if you have zero hydrogens, okay, attached here. So that means this particular carbon should be C double bond O. Understood? And there should be obviously O attached next.
Right.
Clear?
Yes, sir.
Understood? Okay. Look at the next one. There is CH2 here. So CH2 refers to a quartet here. Now, if you look carefully, if I write it like this, CH2 and then CH3. So that means for this particular, and there is oxygen here, right? That oxygen. So for this carbon and the two hydrogens, they are being coupled with these hydrogens, right? Isn't it? So for three hydrogens, what
Right.
is the number of
Yeah.
peaks? So for three hydrogens, the peaks are in the ratio of 1:3:3:1. So therefore, you will get a quartet for this. So which peak is this one? This peak is this one, right? This is the peak here. Clear? Okay. So
Okay.
basically, the number of peaks that you see is defined on how it couples with the hydrogens of the carbon next to it, adjacent to it. Okay. So if there are multiple carbons, you'll add +1 and then you can find the answer. Yes, sir, got my point. Similarly, if you
Yes,
look
sir.
at this one, it is dependent on this peak. How? So because look, there are two hydrogens next to the CH3 group. So that gives a triplet.